The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, we're becoming familiar with the important terms in the Hamiltonian, the rotational term, the spin-orbit term, spin-spin, and spin-rotation. Anything else? And we haven't done much with these two, but once you can write the various operators in a form involving the usual angular momentum operators that appear in the labels of our basis functions, it becomes a trivial matter. And so these are all simple, but I talked about this operator replacement for spin orbit where we take what is a microscopically more honest form for the spin orbit operator and say, well, for the special case where S doesn't change, we can replace this by a constant times some constant times L, and this by some constant times S, and we just have an operator, a constant times L dot S. And this gives us what we need for a lot of the spin orbit matrix elements that we'll encounter. And this operator form is very useful if we have written the matrix, the basis functions in terms of spin orbitals, which we will get to. But it's extremely inconvenient for garden variety calculations, and so you want to replace it. And the form we took for this and for this have already been reduced many years ago, and nobody ever thinks about the true microscopic forms of these unless people really are masochists. So, but the reason I talk about this is that the spin orbit, this form of the spin orbit, A L dot S, is reduced in such a way that it makes people think that you don't have any spin orbit perturbations between states of different spin. And that is wrong. In fact, that's what spin orbit was born for, to mix states of different spin. And so this is convenient, but it's misleading, and there are many textbooks which say this is the spin orbit operator, and then they proceed to talk about matrix elements off diagonal in spin, which you can see is impossible. Or they say that there's no term in the Hamiltonian that changes spin, and that's also wrong. So there's all sorts of stuff in the literature about this that's confusing. Okay, so last time I mostly talked about doublet pi. And we set up the matrix for the doublet pi state in terms of, and we evaluated many of these matrix elements. I alluded in the lecture notes to doublet sigma plus, and I should have completely set up that matrix, but I think that that's a good warm-up task for you. And so we have a matrix, doublet pi, doublet sigma. And we'd like to understand the interaction between doublet pi and doublet sigma. And so what goes in here? And what goes in there are two terms. There are terms that come from the A, 1/2 AL plus S minus, see, I'm writing it down below as I promised I should. And there are terms that come from L uncoupling. And that's minus B J plus L minus plus J minus L plus. Okay, so the terms that result in interactions between doublet pi and doublet sigma involve matrix elements of these operators that we can't evaluate because we lost L. And so we deal with that symbolically, and we say, okay, we're going to have a matrix element V pi doublet pi 1/2 A L plus S minus V sigma doublet sigma plus 1/2. Okay, so L plus raises lambda from 0 to 1. S minus lowers sigma from 1/2 to -1/2. And so we can evaluate the effect of S minus on these basis functions, but we can't evaluate the effect of L plus. And so what we end up doing is just saying we're going to call this alpha V pi V sigma, where this is just an unevaluated constant that expresses the spin orbit interaction between a doublet pi and a doublet sigma. But there's going to be other terms, like when we switch the sign of omega to -1/2, and we switch this to L minus S plus, it would generate another term that looks like alpha. But we have to be careful to discover whether it is this alpha or minus this alpha. And this leads to, this is a very important thing, because you get the wrong answer, you end up getting zero matrix elements when you should have non-zero matrix elements, and non-zero when you should have zero. So this is a very important and subtle point, which mostly you never see. And this matrix element, the one from here, you get V pi doublet pi 3/2 V sigma doublet sigma 1/2. Okay, and what I started doing last time was saying, okay, here are the matrix elements, here are the basis functions. What operator connects between them? And so you can just automatically, by looking at the basis function, say, okay, I need something that raises omega. And that's going to be J minus. And we need something that raises lambda, and that's going to be L plus. So we will get a B of R L plus J minus. And that will be the other matrix element. And we'll just call this one beta V pi V sigma. And again, because it has in it this matrix element of L plus or L minus, yes?
Should the J and the L be reversed in order?
Doesn't matter. They commute. They don't, you know, that's a good point, because normally, since J includes some L, you say, oh, I have to be careful. But one of the results that I wrote in my notes, but I didn't talk about in last lecture, shows that these body components, or these operators that operate on the body frame, do commute. So J components commute with L components, and J components do commute with S components in the body. And that's unexpected, and so you can start to be sloppy here. Okay, so we have these two symbols, alpha and beta, and the reason for alpha is like A, spin orbit, and beta is like B, rotation. And so that's the reason for that notation. Okay, so one point of caution is how do we handle these things when we have states of opposite sign of projection quantum numbers? And then there is the doublet sigma matrix, which I didn't write out, but you will. So we fill in this matrix, and what we find is, I'm not going to write it out, it's in the notes. We find that this matrix does not block diagonalize. For the pi matrix, we had a block that had positive omega and a block that had omega, negative omega, and there were no matrix elements between them. And so just by writing down the matrix, we discovered that there was a kind of a block diagonalization, and if we work out the positive omega block, we really know what's in the negative omega block, and so that we don't really have to do the full matrix. But then when we get to sigma states, it turns out that there is an off-diagonal element between the two signs of omega. And we'd like to make that go away. And we make it go away by going to a parity basis. So parity is an operator that corresponds to reflection in the body frame. It's an operator that commutes with the exact Hamiltonian. That means that it corresponds to a rigorous symmetry. And that means that eigenfunctions of the Hamiltonian can be labeled with the eigenvalues of the operator that commutes with the Hamiltonian. That the Hamiltonian is automatically block diagonalized in the eigenvalues of an operator that commutes with the Hamiltonian. And so we're entitled to construct functions which are eigenfunctions of parity, and that's what we're going to do first today. And then once we do that, we're going to pick up the information about these annoying factors. So, parity. Parity is reflection in the xz plane. Z is always the internuclear axis. Z is almost always the symmetry axis in polyatomic molecules. But we could have chosen the yz plane. For diatomic molecules with cylindrical symmetry, there is no reason for distinguishing between x and y, but it's important to do so because there are some hidden things. You know, the wave functions are, in fact, functions of x and y, and there is some phase interest. So we just sort of have to agree that this is the operator we're going to use to classify for parity. Okay, so our wave function has three factors, j, omega m, and lambda s sigma. And so in order to classify wave functions according to what this operator does to them, we have to apply this operator to each of the three parts. Okay, so vibrations. Vibrations are just like this, and reflection in a plane that contains the internuclear axis, that's clearly not going to do anything to vibrations. So sigma v on the vibrational wave function always gives plus. Now, in order to know what sigma v does to this rotational wave function, this rotational wave function, we have to look at the microscopic form of the wave function. Or we have to say, well, let's just choose a phase convention, see if we can get away with it. And so what we do is we say -1 to the j minus omega. And that's called the Condon and Shortley phase convention. And that choice of phase convention results in j x and j plus minus matrix elements being real and positive. If we had done some other phase convention, then it wouldn't be, you couldn't be sure that jx and j plus minus would both be real and both be positive. So jy is going to be imaginary in this phase convention. So this is the Condon and Shortley phase convention. It's convenient. It's almost always used for functions where you have the magnitude and the body projection. And that's nice. And so over here, we're going to have -1 to the s minus sigma, because we want to emulate the Condon and Shortley phase convention for all parts of the wave function. But then what do we do with the L lambda part? We'd like to write plus L minus lambda, but we don't know what L is. And, excuse me. So we have to do something else. And one solution is to say, well, we don't know what L is, so let's just get rid of it. Just not write it. And the other solution is to make that positive. Lambda is an integer. So going from minus lambda to plus lambda is changing the exponent by 2 times an integer, which is an even integer. And -1 to any even integer is 1. So the big thing is not switching the sign of lambda here, but the big thing is leaving out L. And that's the phase convention that is generally used. And there's one more little thing, and that's a little s. And I'm going to put a little s up here, because there are 2 flavors of sigma states. A sigma state, you know what a sigma orbital is. A sigma orbital is something that has axial symmetry, right? I mean, a sigma orbital you might make from s plus s or p sigma plus p sigma. And so a sigma orbital might look like this. Or you might change the phases. You might have an antibonding sigma orbital. But it's obvious that a sigma orbital has to have positive reflection symmetry in a plane. But you can have sigma states, say, from pi squared. So if you have 2 pi orbitals occupied in a certain way, you can get, well, this configuration gives triplet sigma minus singlet sigma plus and singlet delta. So there is something that's surprising. You can only get sigma minus symmetry from 2 pi orbitals or 2 delta orbitals or 2 phi orbitals. And as long as you build wave functions where the orbital angular momentum of the 2 orbitals are arranged to cancel, you get a sigma state, and you can get these sigma minus states. And so, so when you apply sigma v to lambda greater than 0, it just takes you into a different basis function. It takes you into lambda less than 0. But if you apply sigma v to lambda equals 0, it takes you into something, the same thing. It can't change sigma, but it could give you a -1. And so there is this extra unexpected thing that happens, and we represent it by a little s up here. And s is equal to 0 for all states except sigma minus states, where s is 1. So it's a little fine point, but there are sigma minus states, and you have to worry about them. And so we put that in here. So this then gives us what does sigma v do to the all of the wave functions. We have a -1 to the j plus a half. We have a -1 to the s minus sigma plus lambda plus little s. Okay, and we can simplify this. So we have -1 to the j minus omega plus s minus sigma plus lambda plus little s. And there's an awful lot of stuff here. It would be nice to compress it into a simpler form. So I say that it can be simplified to -1 to the lambda plus little s plus big S minus sigma. Okay, and so what we want to do is find a way to combine these things to get rid of symbols by making even integers. Okay, and so there's lots of ways of doing that. What we really want to do is show that minus omega I guess that's, we just want to, oh, I see what I've done. This is, I've written something that's wrong. Let's just, I'm getting ahead of myself. Okay, so I want to reduce this to -1 to the sigma minus s plus 2 times s minus sigma. Plus little s. Okay, so what have I done here? I have a plus s here, and I want to get to minus s, so I switch the sign of s and I add back 2s. Okay, and now I have we have a sigma here, and I've switched the sign of sigma, so I have to subtract away those, and I have and this is minus lambda minus sigma, and so you just put it all together. I'm sorry, I should be able to do this in my sleep, but once you have this, you have s, which is half integer, minus sigma, which is half integer. So this is an integer. 2 times an integer is an even number. And so we get rid of it. And so the whole thing can be simplified to this more convenient form, sigma minus s plus little s. Okay, so that was just a little detour. Now, so we know what sigma v does to our basis functions. And we're going to first use this to deal with this business of a lambda greater, well, so we'll have a pi state and a sigma state, and we're going to have an L plus here. So this will take sigma to pi, and we're interested in how this symbol can be related to minus pi L minus sigma. So what is the relationship between these symbols? So we have a matrix element of the Hamiltonian. And so this is a number. And we know also that, well, so we have some matrix element of the Hamiltonian. Lambda prime. It's a number. And if we apply sigma v to a number, it doesn't do anything. So we have two things we do. We apply sigma v to the number that this thing is equal to, and it doesn't do anything. And we apply sigma v to each of the parts of this, and we know what it does. And by using that, we can work out what is the relationship between these two things. Okay, so sigma v on, say, L plus. What does that do? Well, L plus is Lx plus I Ly. Lx is y p z minus z p y. Right? Did I get that right? Yep. And sigma v x z takes x into plus x, z into plus z, and y into minus y. So we can work out what sigma v does to each of the components of L. And what we find that sigma v on L plus minus gives plus minus L minus plus. Whoops. Okay? And so you can work that through, and it's really nice because we don't have to look at the differential operators. We just look at the classical mechanical forms of these things. You can write that for L, but not for S. And so you get what the symmetry operator does to the angular momentum. We've already written what sigma v does to each of the basis functions, and so we can put this all together, and what we find is, and I'm going to skip over to the gory details because that's really something that you can do for yourself. And so if we have a matrix element of this form, doublet pi omega L plus and prime doublet sigma plus omega minus 1. So we know what sigma v does to this, we know what sigma v does to this, and we know what sigma v does to that. And so we get minus 1 to the little s plus, I'm just writing down what's in my notes. Okay, so you know that sigma v will take doublet pi omega into doublet pi minus omega with some minus 1 factors. It'll take sigma omega minus 1 into minus omega plus 1. That's what this did. And so we have this stuff. 1 plus 1, that's even. 1/2 plus 1/2, that's odd. 2 omega, well, omega is half integer. So 2 omega is an odd integer. It combines with the 1/2 plus 1/2. And so we end up getting just minus 1 to the little s. And so what you end up finding is that this matrix element is equal to n doublet pi minus omega L minus n prime doublet sigma plus, or let's put it a little s here, n doublet sigma minus omega plus 1. So we have this symbol that looks like it's a beta, but and this looks like a beta, but they're related by minus 1 to the little s. And so for sigma plus states, they are equal. But for sigma minus states, they're minus 1 times, they're related by a sign flip. And that turns out to be incredibly important. And so the general result at the bottom of page 3, it says plus or minus times the matrix element. It should be minus 1 to the little s, the general result. Okay, so this was a detail, but it turned out to be an important detail. And the reason it's important is because we're going to go to a parity basis set. And that block diagonalizes the Hamiltonian. And we really like that. And we're also going to have another packaging. So we have parity, which is expressed by plus or minus 1. And we have E and F, which is a repackaging of the parity concept. And we're going to talk about both of those now. Okay, are we all together on this? I mean, it's not beautiful, but I mean, there are little details that you have to deal with. And I assure you that without having heard this, someday you're going to be looking at a matrix element, and what you're going to discover is all of the things that are supposed to be 0 are not, and all of the things that are supposed to be not 0 are. And you're going to be really annoyed. And it's because of this. And it's because when you're manipulating symbols, sometimes your intuition about what they mean is wrong. And you have to find a way to check without actually looking at the microscopic forms of things, whether you can trust your intuition. And so there's usually a tricky way of being able to do that. And so this is an example. And the example was based on a number not changing when you apply an operator to it. But then the matrix element that is that number is built of an operator and 2 basis functions, and they do change when you apply a symmetry operator. So that's a very useful trick. Okay, so now what we're going to want to do is construct parity functions, because the parity functions enable you to block diagonalize the sigma state and enable you to block diagonalize the world, so that you don't have to write this sextet delta state as a 12 by 12 matrix, but as 2 6 by 6 matrices. And if sextet delta is going to be perturbed by states like sextet pi and sextet sigma through sextet pi, you're going to see that. You're going to do those. It's a simpler calculation. Okay, so we would like to have wave functions which are eigenfunctions of the parity operator, because we're entitled to it. So suppose we define a function psi, which is a linear combination of states, that basis states that have opposite signs of projection quantum numbers. Because that's what this is doing. This is changing the signs of all the projection quantum numbers. And so clearly we're going to want to build something that, in order to make eigenfunctions of the parity operator, we're going to have both signs of all the projection quantum numbers, and we're going to have to build a linear combination of them that gives either +1 or -1 when this operates. Okay, and so we take the square root of 1 over the square root of 2, because there's going to be 2 functions, and we write n lambda s sigma omega j m plus or minus -1 to the j minus big S plus little s n minus lambda s minus sigma minus omega j m. So I've taken all of the projection quantum numbers, and I've switched the signs of all of the projection, body frame projection quantum numbers. I didn't just switch the spatial quantum number. And I have chosen this phase factor here. And so when we do that, what we discover is that oops. I want sigma v operating on that linear combination. So this psi is this thing. And what we're going to discover when we, so when we apply sigma v to this, it gives you that. When you apply sigma v to this, it gives that. And there's a phase factor. And so when you do all of this, you discover that this choice gives eigenfunctions of the parity operator. So this choice, this linear combination of positive and negative projection quantum numbers with this phase factor gives eigenfunctions of the parity operator. And parity can only have two signs. There are only two parities. And so there are these two different eigenvalues. OK, so this is great. And we could stop. We could say, all right, we can now write the parity functions for all states. And for example, a doublet pi state with omega 3/2, and we just put the parity label inside the ket, is 1/√2 times doublet pi 3/2 plus or minus -1 to the j minus s. There's no little s for pi states, or little s for pi states is 0. Doublet pi minus 3/2. So these are the parity states, the parity basis functions for omega equals 3/2. And it's the same thing for omega equals 1/2, because this factor doesn't change. And it's the same thing for doublet sigma, because doublet sigma plus, because again, this factor is the same. So we have the parity functions, and it's not very surprising. The only time you get into trouble is when you have a doublet sigma minus state, and then the parity function, the positive parity function, has a minus sign here instead of a positive sign. So it's only the doublet sigma minus state, or the sigma minus states, that have something special. And you can sort of remember positive omega, negative omega with this factor here. OK, and that is enough. But it turns out it's inconvenient. And, it's inconvenient because in the spectra, or in the energy levels, the parities, so let's just make a little table. So the energy levels for a doublet sigma state, if we write J, 0, 1, 2, 3, parity goes like this. It alternates. And for a doublet sigma minus state, we're going to have pairs of levels. And here I'm going to label them by n instead of j, but we get 0, 1, 2, 3. And what we find is this is plus, this is plus minus, minus plus, plus minus. No, I got it wrong. This is plus, these are both plus, these are both minus, these are both plus, and yep. So we see within sigma states there's an alternating parity. Alternating parity. What is the matter with me? Okay. Minus, minus, plus, plus, minus, minus. So these two things resemble each other, but for every rotational level, there's two rotational levels, and they have two parities. We're going to define a new version of parity, a new packaging of parity, and what we discover when we do that, we're calling it E and F, that all of the levels of a singlet sigma plus state are E levels. And for a pi state, so we'll have J again, 1, 2, 3. The parities would alternate. Oops. But what we have here is E, F, E, F, E, F. So this EF labeling is going to simplify the level diagram in a way that is convenient for making spectral assignments. It's kind of silly. You have one quantity, parity, which is a fundamental quantity. And that parity has a -1 to the j in here. And basically all we're doing is we're taking out this -1 to the j. And by doing that, it provides a labeling which makes it easier for spectroscopists to understand how their spectrum is sampling the energy level diagram. So you have two different things, two different sets of labels to describe the same phenomenon. One is more physical, but less convenient in certain applications. And people just get confused about EF. Okay, so what is the EF label? Are we? No, I'm not criminal yet. So we're going to define EF symmetry by saying the E symmetry is going to be a wave function that under sigma v behaves like this, j minus a half psi E. And for F symmetry, it's minus 1 to the j. So we know what sigma v does to the various signed omega components. And now we're just going to say, okay, we can take we can take this -1 to the j out, and we will then label the states as E that have this property, and as F that have this property. And so at the bottom of page 4, I give the EF labeled doublet pi and doublet sigma plus and minus states. So we can arrange the Hamiltonian either in parity blocks or in EF symmetry blocks. It doesn't matter because the J is always a good quantum number. And so parity and EF differ by a factor of -1 to the J. And so all we're doing is we're going to a parity basis, and we're doing some stuff with signs of off-diagonal elements. And it doesn't change anything. It just leads to a simplification of the level structure, or the labels on the level structure, which turns out to be of enormous value when we try to understand what we see in a spectrum. I mean, basically what you're going to see is that we have P, Q, and R branches, where J changes by -1, 0, and +1. And P and R branches are always E to E, or F to F. And Q is always E to F, or F to E. It's a really, really important simplification. And so and when you have off-diagonal interactions between states, it's always going to be either diagonal in parity or diagonal in EF symmetry. And it's, since the levels are, the parity levels alternate within a group, and the EF doesn't, it's much easier to make a diagram that summarizes what states are going to perturb which states using EF labels than parity labels. You have to just, you know, if you haven't experienced it, you just have to play with it, and you'll discover how wonderful E and F is. And it's an example of, you know, the way you observe something leads you to an optimal way of representing it, which is often not the most physical way of representing it. And so that's probably all I want to say for now. So next time, I will begin dealing with perturbations between different LS states, lambda S states, and second order corrections of the energy levels due to the interactions, say a pi state and a sigma state. They're not perturbing each other, but the sigma state interacts with the pi state in such a way that it causes lambda doublings in the pi state. Or the pi state interacts with the sigma state that produces something that looks like a spin rotation splitting in the sigma state. And so we have now patterns in the spectrum, and we need to understand where these patterns come from. And they come from off-diagonal matrix elements between states labeled with EF symmetry. And there is a procedure for calculating all of these effects, which may look tedious, but it's simple. Okay, so that's it for today.